And you have, I did this years ago in terms of like, I remember some sort of indentation. So I'm trying to rack my brain a little bit. So you have the option of using different indenters, right? Like different geometries makes a difference in terms of what you can measure. And then I assume as well, you have the ability, well, there's differences between materials, like the likely limitations or what you can see, right? Because you do the indentation and then it's an optical piece of data that you analyze. Is that right? On like the specific test of how it works. I see you have one in the back. So
if anyone is on, I guess, on the YouTube channel, you'll be able to see the machine behind me. But what we have is a spherical indenter. So the reason for using a sphere is there's a couple of reasons. So first of all, when we model that test in finite element analysis, we can use the symmetry of the sphere. So we only need to use an axisymmetric model, and that means that the model is much quicker than if you had to use a 3D geometry, and that has huge benefits in terms of we have to run a huge number of these simulations and we have to run them quickly. So that's one huge benefit of a sphere. The second is that it's just a really simple shape. So if you have a sort of a sharp indenter, so for example, a Vickers or a Knoop, or if anyone is familiar with nano indentation, you might use a Berkovich indenter. Now they all have sharp sides. So there's a problem there in the how sharp is that face? And over time, as you keep using that indenter, does it become less sharp or damaged in some way? And that means that you have a little bit of an unknown when you're then trying to model the process. And then finally, a spherical indenter is great because the ones that we use effectively are ball bearings, and they're cheap and widely available. So again, unlike when you go down to super fine scale indentation, nano indentation type stuff, the tips can cost thousands of dollars. We can supply replacements if they do become damaged for any reason for just a few hundred. So we use a spherical indenter. So 1 millimeter radius is our typical size. And then once we've created that indent, we have it's actually a stylus profiler. So that will come across during the test, and it will scan the full shape of that indent. So you've got kind of a spherical part in the center, which of course have been made by the indenter. So we'll get kind of the depth of the indent and the shape of the interior. And then as you come out of the indent, there'll be a pile-up region. So because of the way that metals deform, and actually I probably should have mentioned this closer to the start, we are looking almost exclusively at metallic materials. Because of the kind of fundamentals of, plasticity and how that occurs in metals, so by either dislocation glide or by twinning, you always conserve volume. And that means if you push down with the indenter, you have to push some material elsewhere to effectively conserve that volume. What that means is you get this region around the indent, which is called the pileup region. And depending on how much pileup there is, which we can measure fairly closely, that gives you a really good indicator of how much work hardening the material is going to show. So if there's a low pileup height, you'll get a lower yield stress with more work hardening, which will mean eventually you'll have a big difference between yield and UTS. Or if you have a higher pileup height, low work hardening, and therefore a smaller difference between your yield and UTS. So that's kind of the data that we need. We need the load that we've applied. We need that profile data, and then we put it into our inverse finite element analysis procedure, and that accurately then predicts those properties.
So a lot of your research kind of doing your PhD was on how, like, compiling a bunch of this data and trying to make the model that fits to do this rapidly, or
absolutely,
more efficiently.
So the first couple of things you look at is okay, what do we want to predict? So we want to predict yield stress and work hardening up till an ultimate tensile strength. And then the question is, okay, if we're going to do this by indentation, which is the best outcome for us to look at? So, worldwide, there's people doing a lot of research in the kind of area, and often they'll use the load displacement plot. So you measure during the test load and displacement of the indenter into the specimen. So we spent a lot of time looking at that same data set. And at some point, Bill, my supervisor at the time, said, maybe we should have a look at the effect of looking at the profile. So that shape that we leave in the surface layer after we've done the indent. I said, okay, well, we've spent a lot of time looking at the load displacement curve, but okay, let's have a look at it. And it really was quite surprising. The sensitivity of that outcome, the residual profile, is so much stronger than the load displacement plot. And that was kind of a surprising result. And that was kind of one of the foundations that we've then built the company on. Was we're not going to use the load displacement data. It's kind of difficult to acquire accurately, and it just isn't that sensitive to the outcome that we're interested in. And it was for that reason that we switched to measuring profile data. And yeah, during my PhD, so we spent a lot of time deciding which outcome was best to use. We fixed on the residual profile data, and we published this in scientific journals at the time. And then we kind of went about, as we sort of finished the kind of more research side into forming the company, we looked at then how do we build a machine that could actually automatically do all of this testing. So there was, we kind of recognized there's a lot of people doing different kind of indents out there, but if we said to them, do this test and then find the surface profile, and you can use our software maybe to analyze that data, it would be very messy. We'd be coming in with all different types of data that people would supply, and it could have a significant impact on the outcome. So we kind of realized early on, we're going to have to build this machine ourselves. And as a few material scientists set about trying to sort of conquer this engineering type problem, which, with a little bit of outside support, we have done. And now we have what we think is quite a good looking machine.